The absolute value function, y equals absolute value of x, is a mathematical function that returns the non-negative value of a real number x, regardless of its sign. It is defined as follows: for any real number x, if x is greater than or equal to 0, then absolute value of x equals x. If x is less than 0, then absolute value of x equals negative x. The graph of the absolute value function, y equals absolute value of x, resembles a V shape, centered at the origin, 0, 0. The function is symmetric with respect to the y-axis, meaning that if a, b, is on the graph, a, b, is also on the graph. The steepness of the V shape indicates the rate at which the absolute value increases or decreases as the input value moves away from 0. Let's explore these transformations. Horizontal shift. Shifting the absolute value function horizontally involves adding or subtracting a value within the absolute value bars. For example, y equals absolute value of x plus 2 shifts the graph horizontally 2 units to the left. Y equals absolute value of x minus 2 shifts the graph horizontally 2 units to the right. Vertical shift. Shifting the absolute value function vertically involves adding or subtracting a value outside the absolute value bars. For example, y equals absolute value of x plus 3 shifts the graph vertically 3 units up. Y equals absolute value of x minus 3 shifts the graph vertically 3 units down. Vertical stretch/compression. Stretching or compressing the absolute value function vertically involves multiplying the function by a positive constant. For example, y equals 2 times absolute value of x stretches the graph vertically by a factor of 2, and y equals 1/2 times absolute value of x compresses it vertically by a factor of 1/2. Reflection. Reflecting the absolute value function across the x-axis or y-axis results in a change in the orientation of the graph. For example, y equals negative absolute value of x reflects the graph across the x-axis, changing its concavity. Y equals absolute value of negative x reflects the graph across the y-axis, preserving its concavity. These transformations can be combined and applied together to create more complex changes to the absolute value function. By altering the coefficients and applying shifts, stretches, compressions, and reflections, the graph of the absolute value function can be manipulated to fit various mathematical models and real-world scenarios. Thank you.